Okay, we've reached the final section of this long infinite sequences in series chapter. The final section is on applications of Taylor polynomials. In this video, we're going to go through the first half of this section. And so in the previous section, we were actually introduced to the meaning of a Taylor polynomial, but we didn't expand on it too much from there. So in this section, we're going to talk about, again, what is a Taylor polynomial and how do we use it? And that's primarily what the first half of this section is about. What is a Taylor polynomial and how do you use it? And then in the next video, in the second half of the section, we'll go into more specifics on applications of Taylor polynomials. So, okay, what is a Taylor polynomial? Well, it's really simple. It's just a Taylor series where you're only including the first n terms of the Taylor series. So it's the partial sum of a Taylor series that instead of calling it the partial sum of the Taylor series, it gets its own name, Taylor polynomial. That's it. So in the first half of this chapter, we worked with series where you had, so going from n is equal to 0 to infinity, and then it was some a sub n. Right, the majority of the series we dealt with in this chapter didn't have an x variable in them. Okay, and so we were learning how to test series for convergence and divergence, and most of the series we worked with, again, didn't have an x in them. They were just like this, just a function of n, just the a sub n. Okay, but then we talked about, for all of the convergence testing methods, at the end of those sections, we talked about how, so if you found that a series was convergent, then yeah, ideally, you could come up with a formula for the partial sum of the series, an actual explicit formula, which was S sub n, right? S sub n was it was another sequence where the S sub 1 was the first term, S sub 2 was the first term of a sub n plus the second term, S sub 3 was the first plus second plus third terms of the a sub n. Right, and you can look at that as its own sequence. And if we could actually find an explicit formula for S sub n, then that was ideal, because then we could take the limit as n approaches infinity of that and get the infinite sum that way. We were actually able to find an explicit S sub n formula for the geometric series. And then when you took the limit as n approaches infinity of that, you got the actual infinite sum. And the actual infinite sum was just called S with no subscript n. So this is S. Okay, so, but the majority of series, we weren't able to actually get an S sub n, an explicit S sub n. Like we did that, we were able to do that for the geometric series, there were certain telescoping series where that worked out. Arithmetic series we could, but they weren't convergent going to infinity, but we could still get an S sub n. Right, you could still take an arithmetic series or arithmetic sequence, and plug in. Okay, if you could have an arithmetic series, and you could get an S sub n, and you could plug in any n you want and get the partial sum. Just when n went to infinity, it didn't converge, but still we could get an S sub n. But the majority of series, we couldn't actually get an explicit S sub n. Okay, so what do we do in those cases? Well, we tested the series and saw it was convergent. Now, we couldn't get an explicit S sub n, but you still have the S sub n. It's not like you can't calculate S of any n you want, because we have the A sub n here. Because what is S sub n? S sub n is, you take this and you change n to I, and so that you can put n up here, and then A sub I. That's S sub n. Now, but this is not an explicit formula. Like, you can't take the limit of this and actually evaluate the limit, right? Some function of n, like with, this is not an actual formula. It's a sum. For the geometric series, we got like it was maybe like 1 minus the common ratio to the n over, we got an actual formula for it. Okay, and so with this, what we could do is we could say, well, we can't get the actual infinite sum, but we could get an approximation for it, the infinite sum, by plugging in n is equal to 10 here, n is equal to 100. If you put this into a computer program, then you could put a really big n, okay? So that's the idea of partial sums. We're very familiar with partial sums. But partial sums also apply to the Taylor series, right? Now, it's a little bit different because we're so familiar with working with these partial sums. We got so used to working with them without an x variable, but still, a Taylor series, which is a power series, it's an infinite series. It's going to have a partial sum. So, okay, the Taylor series, let's assume that we've proved that a Taylor series is equal to a certain function, okay, is equal to, and we just do t of x, and that's the sum from n is equal to 0 to infinity, and we know what this is, the nth derivative of the function evaluated at the center point over n factorial x minus a to the n, right? That's the Taylor series. It's an infinite series. It's just a little bit different because it has this x in it, but still. Okay, but just like with this infinite series, we can think about a partial sum of a Taylor series. We can, instead of summing infinite of these terms that have x's in them, we can say we're going to do just the first n terms. So we change this I into an I, and that's it. You specify an n. The idea is if you said n is equal to 3, you would take the first 3 terms of the Taylor series and sum those. They would have, each term would have an x in it, or maybe not the first term, but most of the terms would have an x in it. That's the partial sum of a Taylor series. And this is what's called the Taylor polynomial. The S sub n's don't get their own special name, but this gets its own special name, Taylor polynomial. And I guess they call it that because it's, once you actually restrict the terms to a finite number of terms, then it's technically, it's a technical polynomial. Okay? So that's the Taylor polynomial. Okay, now, in addition to like the infinite sum S and the partial sum S sub n, we also talked about R sub n. Okay, so now note that we can only say that this is equal to S. And we can only say that like the Taylor series with no subscript is equal to a sum. It has to be convergent. You can't say that if this wasn't convergent, you can't say it's equal to S. And when you say the Taylor series is equal to a function, it's equal to a sum, it's specifically over the interval of convergence. When you plug in an S, it's convergent. Okay, so that's important to note, right? So like the Taylor series is not equal to the function outside of the interval of convergence. Okay, so we talked about how if we wanted to get, we'd like to be able to know how accurate, we plug in an n is equal to 10, 100, how accurate is that to how close is the sum we get with S sub n to the actual sum? So we can get a sense of the error, right? And so that's what R sub n was all about. And the meaning of R sub n is, so S, the infinite sum, is equal to S sub n plus R sub n. So it depends on the n. So if we plugged in n is equal to 10, okay, we get a number. But we're only summing the first 10 terms. And we're leaving off the term 11 to infinity. Well, the sum of term 11 to term infinity, that's R sub 10, not 11, R sub 10. If we plugged in S is equal to 50, then you sum the first 50 terms of the infinite series, that's S sub 50, and then the sum of term 51 to infinity, that's R sub 50. Okay, and so you can see with that, if you can get, we could never actually solve for what exactly R sub n was equal to, because then if we could, then we wouldn't even need to use S sub n. We would just get what we wanted in the beginning, S. So we could never actually figure out what exactly R sub n was equal to, but we could get an estimate of how large of its ceiling. It can't be bigger than this value, so we could see worst case scenario how far off we were S sub n was from S. Okay, we had methods of estimating the size of R sub n for the integral test, for the comparison test, for the alternating series test. Okay, but this same concept we extend to Taylor series and Taylor polynomials. So the Taylor series, the infinite series, is equal to the Taylor polynomial plus then R sub n of x. Same idea, right? But this is a little more confusing because we have the x in there, right? We didn't have an x in the first half of the chapter, so now we have an x. So the R sub n depends on both the n that you choose, right? So if you choose a big n, a large n, you're going to have a smaller R sub n, right? The bigger the n you choose. But also the x you choose, the farther you are away from the center point, then the larger R sub n would be. Okay? And so with Taylor polynomials, if we want to use a Taylor polynomial of a function, then to see how accurate the use of the Taylor polynomial is, we're going to use R sub n of x. And we talked about how do you find like an upper bound on how big R sub n of x is. That's what Taylor's inequality is all about. Okay, so in this section, we explore two types of applications of Taylor polynomials. First, we look at how they are used to approximate functions. Computer scientists like them because polynomials are the simplest of functions. Then we investigate how physicists and engineers use them in such fields as relativity, optics, black body radiation, electric dipoles, the velocity of water waves, and building highways across a desert. So yeah, what we're looking at here in the first half of this section is, you'll see this in research papers and certain books and in different situations where a function is represented by the first 2, 3, or 4 terms of its Taylor series. So it's represented by a Taylor polynomial. And the reason why this is done is it might be difficult or impossible to differentiate a certain function, but you can differentiate its Taylor polynomial. But there's other reasons past that, with partial differential equations, there's different situations where you're going to be using Taylor polynomials. There's definitely circumstances in physics, engineering, etc., where it's very helpful to represent a function by one of its Taylor polynomials. Okay, so what you can imagine, though, is whenever you're wanting to do this, you'd really like to know how many terms you need to use to get a certain accuracy. Okay, and so that's what the R sub n is for. So, okay, suppose that f of x is equal to the sum of its Taylor series at A. So there you go. F of x is equal to, the general Taylor series. In the previous section, we introduced the notation for T sub n of x for the nth partial sum of this series and called it the nth degree Taylor polynomial of the function at A, right? So the Taylor polynomial, it's technically the Taylor polynomial of a function, but at a certain center point. Okay, so there's the Taylor polynomial, right? You just replace the Taylor series summation, replace the n with I, so you can sum not to infinity but to n, and now the n is replaced in I in the a sub n is turned into an a sub I, and then there you go. It goes all the way not to infinity, but it goes all the way to n, to the a sub n. It goes all the way to a sub n. Okay, since f is the sum of its Taylor series, we know that as that T sub n of x approaches f of x as n approaches infinity. So yeah, the S sub n, right? The S sub n, you forget about Taylor series, like there's no x here, but the meaning of S sub n, like whether or not you have an explicit formula for S sub n or you just have the summation, when you take the limit as n goes to infinity, that's another way of defining the infinite series, right? I had the S sub n formula written out that's another way of looking at the definition of an infinite series. You take the limit as n goes to infinity of the s of n. Okay, and so that's why we know that the partial sum can be used to approximate the infinite sum, which the infinite sum in this case is the function. Right? We've proved that the function is equal to its Taylor series. We've gotten past that point. So the function is equal to its Taylor series, and so you know that. So an approximation for the function is the Taylor polynomial. Okay, notice that the first degree Taylor polynomial, so t sub 1, is the function evaluated at a plus the first derivative evaluated at a times x minus a. What is this? This, if you think back to the linear approximations and differentials section, this is the linear approximation, right? This is the same as the linearization of the function at a that we discussed in chapter 3. So why does this make sense? Well, because this is the equation for the tangent line to the function f at a. This is the equation of the tangent line. That's what t sub 1 is. Okay, so if we come here, here's the function y is equal to x, or e to the x, and there's t sub 1, the tangent line to e to the x at x is equal to 0. That's the first degree Taylor polynomial approximation for the function e to the x at x is equal to 0, is the tangent line to e to the x at x is equal to 0. Okay, and the properties of the first degree Taylor polynomial are that the function itself and the first derivative of the function evaluated at the center point are both equal. So if you plug in the center point into the function and you plug the center point into t sub 1 of x, you get the same value. And if you plug in the center point into the first derivative of the function and the center point into the first derivative of t sub 1 of x, they match up. You get the same value. But any higher derivatives, that's not the case. Okay, and so with that, you can see that in general, the idea is it can be shown that the derivatives of t sub n at a agree with those of the function up to and including the derivatives of order n. So that's another way of looking at the meaning of the Taylor series. I mean, that is we saw in the derivation of the Taylor series formula that that's how it worked. But for the Taylor polynomial, the idea is the more terms you use, the higher n, then you're saying that the derivatives of the function up to that n, if you plug in the center point, that they match up with the actual function. The higher the n, then the more of those matching up derivatives you have. And so they illustrate this with, so if we go to t sub 3, what happens? Or t sub 2. If you go to t sub 2, what happens? Well, then the function evaluated at the center point is equal to the Taylor series at the center point. The first derivative of the function evaluated at the center point is equal to the first derivative of not the Taylor series, the Taylor polynomial, t sub 2 at the center point. And the second derivative of the function evaluated at the center point is equal to the t sub 2 second derivative evaluated at the center point. But then any higher derivatives, there's no match. So what you get, though, is you get the pink was e to the x. Yeah, you get, so t sub 2 is this parabola here. Instead of a line being the approximation for the function at a certain point, you get, with t sub 2, you get a parabola. And then t sub 3, you'll get a cubic. And you can see, though, if you look closely around the point, far away from the point, the parabola goes off away from the function. Same thing with the cubic. But around the point, it's as n gets higher, as the number of matching derivatives get higher, it's hugging the curve better and better. And again, the meaning of that is the better that it's hugging the curve is because there's more derivatives that match. There's more, when you plug in the center point into the function, or either the function and the Taylor polynomial, as well as certain derivatives of the function in the Taylor polynomial, you have more of those where the Taylor polynomial and the function match. The higher the n, the more derivatives are matching. Okay, and then as we know, as n goes to infinity, then the Taylor polynomial is going to line up exactly with the e to the x curve. Exactly, as n goes to infinity. Okay, the values in the table here give a numerical demonstration of the convergence of the Taylor polynomial to the function y is equal to e to the x. So yeah, this table is about this here. Okay, we see that when x is equal to 0.2, the convergence is very rapid, but when x is equal to 3, it is somewhat slower. In fact, the farther x is from 0, the more slowly t sub n of x converges to e to the x. So yeah, this is all about, we're talking about the Maclaurin series of e to the x. Well, Maclaurin polynomials, you could say. Okay, but they're, so when it comes to Taylor polynomials or Maclaurin polynomials, there's two variables, right? There's the n that you use, but there's also the x that you choose. And so what they're comparing here is they're choosing an x that's close to 0, closer than this is, right? This is farther away, this is closer. And then they're showing how they are both converging as n gets higher. So they're converging to different values, right? Because this is converging to e to the 0.2. This is converging to e to the 0.3. Here's the value of e to the x. So they're both converging, but this is going to converge quicker because it's closer to the center point. But, it's interesting to note, though, like they say that it might have been a better idea to use a Taylor polynomial centered at 3. But when it comes to, we've talked about this, if you have like a radius of convergence, a Taylor series with a radius of convergence that's equal to infinity, you can plug in any x you want, like e to the x, for example. Well, you could use the Maclaurin series for whatever value you wanted to evaluate e to the x at, as long as you're willing to use enough of the n's, a high enough n, right? So like you could think about if you had a computer program, then you could use a high n. If you wanted to do e to the 50, you could use the Maclaurin series for e to the 50, with x equal to 50. You're just gonna have to use a higher n value. Now, this isn't the case in general, because, yeah, it's the case where you could hypothetically use the Maclaurin series for any function you want to approximate, no matter what, if, or the Maclaurin polynomial, if you were, the radius of convergence was infinity. But, we saw a lot of examples, like for the natural logs, etc., where the radius of convergence is only 1. So you can't go past plus or minus 1 from 0. So if you wanted to put x is equal to 3 into that function, you would have to redetermine the Taylor polynomials at a different center point. So, but then there's also the case that if you're actually, if you're going to be using the Taylor polynomial because it's easier to differentiate or something, well, then maybe you don't want to do e to the x. Like if you wanted to do e to the x evaluated at 3, maybe you don't want to write in your paper, you don't want to write out 7 or 8 terms of the Taylor polynomial, right? If you're just inputting an x into a computer program and getting the value out, then who cares if you have an extra 7 or 8 terms or more than that? But if you're actually going to be writing the Taylor polynomial in a paper and doing like a differentiation and then maybe you don't want to have all these terms. You'd rather just go ahead and redefine the center point, so you'd only have to use a few terms. So it just depends on the application. Okay, so when using a Taylor polynomial to approximate a function f, we have to ask the question, how good of an approximation is it? Of course. How large should we take n to be in order to achieve a desired accuracy? So to answer this question, we need to get an estimate for the remainder, right? Well, the absolute value of the remainder. So maybe the t sub n, it's when we evaluate it at a certain x, maybe it's above or below the actual value. But we just care about how far above or below we are. And so that's what r sub n is all about, right? The absolute value of r sub n of x is equal to what? It's the absolute value of the function minus the Taylor polynomial at that n value and x value. Right, it's a little confusing. There's two variables here, the n and the x. But just the distance from you plug in the x to the actual function, and then how far is that from when you plug in x into the Taylor polynomial with whatever n you chose. The absolute value of that. That's the actual error, and that's what r sub n is. R sub n is the actual literal error but we get an estimation on how big R sub n is. Okay, and so how do we get an estimate on the size of R sub n? Well, that's what Taylor's inequality is all about, which we learned in the previous section, because there's two uses of Taylor's inequality. In other words, there's two uses of this R sub n of x. One is you take the limit as n goes to infinity of this, and if it's equal to 0, that proves that the function is equal to its Taylor series. Okay, and then the other use is what we're doing here, to see how accurate a Taylor polynomial is at a certain value of n. Okay, there are three possible methods for estimating the size of the error. So one is case 3, you use Taylor's inequality to get the size of the R sub n, right? But the first method it shows here, all you do is you just graph the R sub n of x, because if you're using Taylor's polynomial to approximate a function, you can think about, in a lot of circumstances, you already have the function. So if you have the function, well, then you can just use Excel or whatever program you have to get f of x minus the whatever t sub n you're using. Get that absolute value. That's what R sub n of x is, the absolute value. So just graph it. If this is simple to do, then why not do this? In this case, you could actually get the exact value of R sub n of x. Okay, but it won't always be the case that you actually have the function. You could get the exact value of R sub n of x. Either that, or maybe this is too complicated to do for some reason. Okay, so what else you can do is, it says if the series happens to be an alternating series, we can use the alternating series estimation theorem. Now, I'm not sure why they only included the alternating series estimation theorem, because you could say, well, then why don't you use the integral test estimation theorem or the comparison test estimation theorem for R sub n? Well, like if you have an alternating series, you can't use the integral test or the comparison test. But I'm saying, okay, what if you don't have an alternating series? Why don't you use the integral test remainder estimate or the comparison test remainder estimate? And I looked into this briefly, and you're welcome to look into this on your own, but it seems that you could, if you wanted to, you could use if you didn't have an alternating series, if your Taylor series wasn't an alternating series, you could use those error estimates for R sub n, assuming that the series you have, the Taylor series you have, qualifies for those tests. And it depends on at whatever x value, right? There's two variables. It's does it qualify for the integral test or the comparison test? If it does, well, at which x values does it qualify? But so I think you could do that, but I think it's kind of complicated when you have to consider for which x values does it qualify. Whereas with the alternating series test, the only qualification is, well, no, there is a qualification that the b sub n plus 1, it needs to be always decreasing. So, I'm not sure why they only mention the alternating series estimation theorem here. Maybe because it's really simple, right? With the alternating series test, it's just, so you have the a sub n, but then the b sub n is just the absolute value. It's like the positive part of the alternating of the a sub n. And the R sub n is just always going to be less than or equal to the b sub n plus 1. It's really simple. So maybe that's the only reason they included the alternating series estimation theorem as an option. But it seems to me if you wanted to, you could graph it like this and get an actual exact value for R sub n. You could use any of the R sub n estimation methods, whether it be with the integral test, the comparison test, or the alternating series test, assuming that at certain whatever values of x you're using it for, the series qualifies for those tests. Or you could just use Taylor's inequality. Okay, so with that, let's take a look at a couple of examples. It says approximate the function cube root of x by Taylor polynomial of degree 2 at center point 8. So the idea is we're going to be plugging in values of x into f of x is equal to cube root of x around x is equal to 8. So we want to center the Taylor polynomial at 8. Okay, then it says, how accurate is this approximation when x is between 9 and 7? So if we were going to restrict the inputs that we're going to be inputting to an x between 9 and 7 inclusive, 7 and 9 inclusive, then how accurate will the approximation be? So we're going to say n is equal to 2. If n is equal to 2 and we're plugging in values between 7 and 9, centered at 8, and plugging in values between 7 and 9, how accurate is our Taylor polynomial going to be? Okay, so they do the standard method here. We're building this from scratch, from the definition of the Taylor polynomial. So here's the first. So 1, 2. Okay, yeah, so they go to the third derivative because we're going to need this for either if this is an alternating series, for the alternating series error estimation, or for Taylor's inequality. Okay, but they only plug in the center point 8 for the first 3 derivatives, or the first 2 derivatives and just the function, 0, 1, and 2. The 0th derivative, the first derivative, the second derivative. Okay, so then they write out so that's it. We don't have to find a pattern or anything and come up with a summation, because there is no summation. It's the Taylor polynomial. They just write out the first 3 terms. There you go. Right? We're not coming up with the Taylor series. So what we're saying is the cube root of x is approximately equal to t sub 2 of x, and notice how they don't put the center point, right? With the Taylor series, the notation for the Taylor series, or for a Taylor polynomial, there's no center. You don't ever indicate the center point. And the reason why you can think about it is because, I think the reason why they do that is because in general, as n goes to infinity, it doesn't matter what the center point is, right? Like, it kind of does if it depends on if the radius of convergence is not infinity. But I think even so, you still don't indicate the center point when it comes to the t of x or t sub n of x or whatever, because it's like with e to the x, right? If you have e to the x centered at 0, you get a Maclaurin series. If you have e to the x centered at 10, you get another Maclaurin series. But as n goes to infinity, they're both e to the x, right? So I think it's in that sense why they don't put, you have t sub e, the cube root of x is approximately equal to t sub 2 of x, and we're centered at 8, but they don't indicate that here. Only in the actual expansion of the Taylor polynomial do you see where it's centered. Okay, but what we're doing is we're saying the cube root of x is approximately equal to this. We could plug in 0 here. I think that's another reason why, because it's centered at 8, but it's not like we couldn't plug in 0 where the Maclaurin series would be centered. We could plug in 0, right? This is an approximation for the cube root of x at, I guess it would be any x. I don't know what the radius of convergence of the Taylor series of the cube root of x is, but, you could think about it, though, it could be for any x, right? In general, you could think about a Taylor series that way. Okay, so we've answered part A. We've approximated the function, the cube root of x, with a second degree Taylor polynomial centered at 8. Okay, now we want to find out how accurate is this if we're going to restrict the x inputs to be between 7 and 9. Okay, the Taylor series is not alternating when x is less than 8, so we can't use the alternating series estimation theorem in this example. So yeah, what they said there was that if for any x value between 7 and 9, no matter what you plugged in, you would get an alternating series. So we're thinking about the series. Now, when it comes to the R sub n estimation, we're bringing in the series as part of our thought process, because we're estimating how accurate is the Taylor polynomial relative to the infinite series, the Taylor series, because that's equal to the function. The function is equal to the cube root of x. Or no, the Taylor series is equal to the cube root of x. So we're trying to see how close is this to the series, the Taylor series, which is the function. Okay, so the Taylor series, the infinite Taylor series, we can see that for any value of x between 7 and 9, it's not going to be alternating. If x was greater than 8, it would be. You can see you're going let's see, it goes positive, positive, minus, so, well, okay, if x is less than 8, then you got negative here, and then this is positive. Yeah, so you need, with alternating series, you need every other term to be switching sides, and for all values between 7 and 9, that's not the case. So we can't use the alternating series estimation theorem in this example, but we can use Taylor's inequality with, so they do, so let's come here. Here's Taylor's inequality. They're going to plug in n is equal to 2, okay, and you get an a is equal to 8, right? And so this fills out, however, you don't have the capital M. Taylor's inequality is all about getting this capital M. You're going to know, because if you look here, you know what n is, you choose n. You know what a is, you chose a. So it's just what is capital M. Once you have capital M, then you've got the estimation for the R sub n. So capital M comes from this, and that's, we need the nth plus 1 derivative. And so that's this here. The absolute value of this for any x between 7 and 9 is that no matter what x you put in, is the absolute value of this always less than or equal to a certain number. Okay, so they plugged in n is equal to 2 and a is equal to 8, and they simplify, got this. And now, so the n plus 1th derivative, here's the third derivative, and it's going to be the case that the lower the x value, the higher this is going to be, because you've got it's in the denominator, the x is in the denominator. Okay, so 7 is the lowest value you could possibly plug in is 7, so they plug 7 in here, and that's it. F triple prime of x, for if you're restricting x to be between 7 and 9, f triple prime of x will always be less than 0.021 or 0.0021, no matter what. So capital M is equal to 0.0021. Okay, so they plug this capital M in here. All right, now we can simplify this further, though, because we have an actual restriction on x. Like x must be between 7 and 9. So we can think about, okay, what value of x would make this x minus 8, the absolute value of x minus 8 cubed, the largest. Now, it's not like we have to choose the same x value that we chose for the m, right? These are two kind of different questions. So if they subtract 8 from both sides here to get x minus 8, okay, but the absolute value of x minus 8 then is going to be, it's going to turn this into a 0, so that means they plug in 1 here, right? That's the largest. If x is restricted to be between 7 and 9, that's the largest the absolute value of x minus 8 can be. And so you've got the capital M here, and now this is turned into 1 cubed, and over then divided by 3 factorial, and they get the absolute value of R sub 2 of x is going to be less than 0.0004. And there you go. Thus, if x is restricted to be between 7 and 9, then the second degree Taylor polynomial of the cube root of x centered at 8 is going to be accurate to within 0.0004, no matter what any x you choose between 7 and 9. Okay, it says let's use a graphing device to check the calculation in example 1. So here what they're doing is they're graphing. So here's the cube root of x. Here's the second degree Taylor polynomial, right? You can graph both of those, and this is from 0 to 15. But what they're going to do is they're going to change the interval from 7 to 9, zoom in, and then just take cube root of x minus t sub 2, and then take the absolute value of that. And there it is, the absolute value of r sub 2 of x from 7 to 9. And so the largest, you can see the largest that r sub 2 of x can be shown graphically is 0.0003. That's the exact answer. That's the largest that r sub 2 of x could actually be, the absolute value of it. That's the exact answer. Now, again, why wouldn't you just do this? I mean, what's the point of Taylor's inequality? They're just trying to illustrate, give you a full view of this. Maybe you can't, or it's not easy to do this graph. But still, you can see Taylor's inequality did a good job. It was 0.0004. This is 0.0003. Thus, the error estimate from graphical methods is slightly better than the error estimate from Taylor's inequality in this case. Okay, example 2. What is the maximum error possible in using this approximation? So this is the first 3 terms of the Maclaurin series of sine x. Okay, so if we're going to use this to approximate sine x, then what's the maximum possible error if we're going to be using an x that's between minus 0.3 and 0.3, all right? And then we're going to use this approximation to find sine of 12 degrees, correct to 6 decimal places. And then we want to find for what values of x is this approximation accurate to within 0.00005. All right, so the first thing I want to talk about here is that the notation for Taylor polynomials can get a little confusing, because this is a situation where when we're developing this Taylor series, this is one of the cases where we have 0 terms, right? Like you can see the x to the 0 is missing, the x to the second is missing, the x to the fourth is missing. And so the question is, the way we looked at S sub n, the partial sum S sub n, the way it's described is you're summing the first n terms of the sequence, right? That's the way you look at it, and that's a good way to look at it, but it's confusing when it comes to Taylor polynomials, because, you would be tempted to say, well, okay, this is equal to, as far as sine of x, the Maclaurin series of sine of x, this is t sub 3, right? We're summing the first 3 terms of the Maclaurin series of sine x. Okay, but the ambiguity comes in for 2 reasons. So first, so here's the Maclaurin series for sine x, and so we know that this is equal to, if you write it as a summation, n is equal to 0 to infinity, so minus 1 to the n, x to the 2n plus 1. Okay, the first thing that's confusing is that it's not like if we want to, so n is equal to 0, we get x. But it's not like if we want to get to the second term, we plug in n is equal to 2, we skip an n, right? No, we go to n is equal to 1, and we get the second term. We get x cubed over 3 factorial. Then we go to n is equal to 2, we get the third term. So from this perspective, it is kind of like, well, you just, for the t sub n, you just plug in, here, this would be t sub 2, right? From the perspective of the summation, then we should put t sub 2 here. But then that's kind of confusing because, well, all right, if the summation starts at n is equal to 1, then you just plug in the n and you're summing the first whatever terms, right? If this started at n is equal to 1, then you say t sub 3, you're summing the first 3 terms. But now that we're starting at 0, okay, you could plug in t sub 2, and that's correct, but you're not summing the first 2 terms, you're summing the first 3 terms. So what's the official way to view the notation for Taylor polynomials? Well, so, okay, if we've got t sub n of x, the n is going to correspond to the order of the Taylor polynomial, or the degree of the Taylor polynomial. That's the way it works, no matter what, for in all cases. Therefore, this here, this is t sub 5. Okay? Which is, again, it's confusing because we're not summing the first 5 terms. But, even if we didn't have terms that were 0 terms, it still could be confusing if the summation is starting at n is equal to 0, because, you're not necessarily summing the first n terms, whatever you put for n anyway. So the way you're going to do it is just when you have the Taylor polynomial, you write out however many terms, you're going to sum the first whatever terms, and then it's t sub the order. the order of the polynomial. That's the way it works. Okay, so let's get started with the problem. It says, notice that the Maclaurin series is alternating for all non-zero values of x. Okay, so it says it's alternating for all non-zero values of x, plus, minus, but then you might wonder, well, what about if there was a negative value of x? So if it's a negative value, yeah, all these powers are odd, so it just stays negative, but then you get plus, minus. So the first two terms are plus, or positive, that's not alternating. Well, okay, remember, when we're thinking about the R sub n estimation, that's what we're doing here, right? We're dealing with the R sub n estimation. That's something that's concerned with the going to infinity. It's kind of like with the convergence tests. For the convergence test to be applicable, it didn't have to start at n is equal to 1 or 2 or whatever. It was all about just if you can find any n term, no matter where it's at, and then from that term going all the way to infinity, the rules are followed, then you can apply that test. Same thing here. As long as, so no matter if the x is negative or positive, you can see starting from this term, it's going to be alternating all the way to infinity. So it is an alternating series in that sense. Okay, now, but to qualify for the alternating series test, you need to have successive terms be decreasing in size. And this is the case for when the absolute value of x is less than 1. And this is important because, you know, with sine x, the radius of convergence for the series is all real numbers. Okay, so in general, you can't just apply the alternating series test here, but since we're restricted to this interval, it's okay. But in general, you'd have to do the Taylor's inequality. Okay, but we're going to use the alternating series estimation theorem. It says, so how do we apply the alternating series estimation theorem? We look at the this is here, the notation is going to get confusing again. We look at we're using a certain partial sum with a certain number of terms. Okay, and we check the next term that we didn't include in the partial sum. The absolute value of that term is going to be the ceiling on the error. And so they call this, in the alternating series estimation theorem, they call this b sub n plus 1, and the b sub n is like the absolute value of the alternating series. So you just kind of remove that minus 1 to the n, and you're left with the b sub n. And the absolute value of the b sub n plus 1 term, that's the ceiling on the R sub n. But the notation is confusing here because of again, we're doing t sub 5. So we want to do the n is equal to 6. We want to look at the sixth term. Well, okay, from the perspective of this, I guess we can think about the sixth term, right? So 0, 1, 2, 3, 4, 5. When n is equal to 5, you get, well, okay, we can't plug in n is equal to 6 into here. Okay, let's say n is equal to 5. That's the sixth term because we start at 0. So n is equal to 5. That's x to the 11th. That's not right. So how are we supposed to look at this? So you're just going to think about the meaning of the alternating series estimation theorem. All right, and it's just it's the next term you're not including in the partial sum. So we know if we come here, what's the next term? What's the next term? It's that x to the 7th over 7 factorial. So we take the absolute value of that, and that's going to be the ceiling on the error. So the 7 factorial is always positive, so they put the absolute value here. And so this is the ceiling. We're restricting the x values to be between plus and minus 1, or else we couldn't use this theorem, this alternating series error estimation theorem. Okay? And so if that's the case, then if we're using t sub 5, then this is going to be the ceiling on the error, which is the distance that our Taylor polynomial value is away from the actual sine of x value. All right? But so it depends on the value of x we picked, though. If we pick the center point 0, then there is no error, but for any value away from 0, there's going to be some error. And we're going to be, we know we're plus or minus 0.3 away from the center point, according to our criteria. Well, we can see that if we plug in 0.3 or negative 0.3, that's the biggest that this can get. there's no other value within the interval from minus 0.3 to 0.3 that could make this bigger than the endpoints at 0.3 or minus 0.3. So they just plug that in, and there you go. Boom. We've answered the first part of part A. This is the maximum error possible if we're using the T sub 5 Taylor polynomial for the Maclaurin series of sine x, and we're going to input an x value between minus 0.3 and 0.3. Okay, so next it says we want to use the approximation to find sine of 12 degrees. Use the T sub 5. Okay, well, you might say, well, wait a minute, 12 degrees, that's 12. That's outside of the minus 0.3 to 0.3. Well, remember, we developed the Taylor polynomial using derivatives that, all of those derivatives we assumed were the trig functions were in radians. So the input into the Taylor polynomial is going to need to be in radians. So when we convert 12 degrees to radians, that's 12 degrees to radians is pi over 15. Pi over 15 is less than 0.3. So they plug pi over 15 into the Taylor polynomial, T sub 5 polynomial, and there you go. This is accurate. If you plugged in sine of pi over 15 into your calculator, the result would be within 4.3 times 10 to the minus 8 of this. And that's better than 6 decimal places. All right. So now part B, it says, for what values of x is this approximation accurate to within 0.00005? So this approximation, the Taylor polynomial. All right, well, if we come here, this error, maximum error here, 0.00005 is greater than this. So we don't need to use a larger n value for the polynomial. We can get that accuracy, that 0.00005 accuracy with the current Taylor polynomial that we have. And in fact, since it's less strict, we can see that the interval, the x value interval, the minus 0.3 to 0.3 is going to increase because we don't have to be this accurate. So how do we figure that out? Well, this is the ceiling right here on the T sub 5 Taylor polynomial. This is the ceiling. So just set this less than, so just solve this inequality. This needs to be less than 0.00005 and solve for x. And you see, that's what they do here. Okay, they solve for x and get 0.821. So the interval increased from minus 0.3 to 0.3 to minus 0.821 to 0.821. So if you plug in any x value in that range into the T sub 5 Taylor polynomial, then you're going to be accurate to within 0.00005, no matter what value you plug in. Accurate as far as comparing that to plugging in sine of that x value, plugging that x value into the actual sine function. Okay, so now it asks, what if we used Taylor's inequality as opposed to the alternating series estimation, error estimation? Okay, but again, here the notation gets a little confusing because, all right, so Taylor's inequality, you first find what m is, so it's the n plus 1th derivative of x. The absolute value of that is going to be less than or equal to m for all x over an interval. So we're thinking about all x over, we actually chose an interval from minus 0.3 to 0.3. Okay, and then once you have this m, then the absolute value of r sub n of x is less than or equal to, so you've got n plus 1, and then, okay, so how does the notation work here, right? With the T sub, we have T sub 5. Okay, so with Taylor's inequality, you're thinking about Taylor polynomials. Okay, so you might say, okay, well, great, then, so we've got T sub 5, so go ahead and plug in n is equal to 5. Well, no, actually, we're not going to do that because if we plugged in n is equal to 5, we get that there's the sixth derivative, the term associated with the sixth derivative for the Maclaurin series is a 0 term. So it's kind of similar to the alternating series theorem in that we want to work with Taylor's inequality here with the next non-zero term, which we know is associated with the 7th derivative. We go from the 5th derivative term to the 7th derivative term. So we want to plug in n is equal to 6 into the entire Taylor inequality theorem. N is equal to 6. So the seventh derivative, that's how you find m. And then you plug in 6 here. So this is going to be 7 factorial. This is going to be the absolute value of x minus a to the 7th. Okay, so it gets the 7th derivative is minus cosine x. And for all x, in any x you plug in, that the absolute value that's going to be less than or equal to 1. So m is equal to 1. So they plug that into the Taylor's inequality theorem. You have r sub 6 of x, the absolute value, is less than or equal to 1 over 7 factorial times the absolute value of, then the center point is 0, a is equal to 0, so absolute value of x to the 7th. So there you go. And they say that if we compare this to what we got with the alternating series estimation theorem, we got the exact same thing. This is absolute value of x to the 7th over 7 factorial. That was the ceiling on the r sub n. Right? This is the ceiling on the r sub n. Okay, so now it says, what about the graphical method? So here's the absolute value of r sub n of x, and you can graph sine of x, and so you say sine of x minus, here's t sub 5, the Taylor polynomial. That you take the absolute value of that, and you graph it, and they graph it on the interval from minus 0.3 to 0.3. So there it is. There's the absolute value of r sub n of x. What's the max possible error? Well, at the endpoints, it's 4.3 times 10 to the minus 8, and that actually happens to be the exact same thing we found with Taylor's inequality and the alternating series theorem. But with the first example, it didn't work out that way. Actually, the graphical method, which gives you the exact error value, was a little bit different than what we found with Taylor's inequality. Here, they're the same. Okay, but note that it doesn't have to be the max value won't always be at the endpoints. It could be something like this. Maybe it takes place, the error is largest at the middle of the interval. Okay, now for part B, it says we wanted the x values, the interval of x values that corresponds to a maximum error of 0.00005. So all they do is they extend this interval, this minus 0.3 to 0.3, out to minus 1 to 1, and then draw a vertical line at or a horizontal line at 0.00005, and with that they can get the new interval, and it ends up coming out to the exact same. It was 0.821, the exact same value that the Taylor's inequality and the alternating series theorem found. Okay, now it says if we had been asked to approximate sine of 72 degrees instead of sine of 12 degrees in this example, it would have been wise to use the Taylor polynomials at a is equal to pi over 3 instead of a is equal to 0, because they are better approximations to sine of x for values of x close to pi over 3. Yeah, so it depends on the application, but in general, you want the center point to be as close as possible to the value you're going to be evaluating the function at, ideally. But it says, notice that 72 degrees is close to 60 degrees. So yeah, if we wanted to do sine of 72 degrees, it's not like you'd want to center it at sine of 70. Would you do that? Would we want to center it at sine of 70? No, you want to center it at a value that works well with the function. So pi over 3 is a special angle, right? It's 30, 60, 45. So pi over 3 would be great because everything would be much cleaner. Plugging pi over 3 into the sine and cosine functions is a lot cleaner. Okay. Figure 6 shows the graphs of the Maclaurin polynomial approximations. So, okay, yeah, here's a graph of the first 4 Taylor polynomials of the sine of x Maclaurin series. So yeah, here's t sub 1, t sub 3, t sub 5, t sub 7. And the corresponding graphs along with sine x here in red. And so, yeah, the idea is with what you're going to notice as n gets bigger and bigger and bigger with the Taylor polynomial is, so if you zoom in on the center point, so the center point here is at 0, but it can be anywhere. If you zoom in on the center point, you can think about how, even with a linear approximation, we've talked about in the derivative section, if you zoom in really close to a function, even if it's a really curved function, if you zoom in close enough, it looks like a line, right? And so in that sense, the linear approximation t sub 1 is going to, if you zoom in close enough, it's going to hug the curve very well, right? And the way you think about the Taylor polynomials is that as n gets bigger, so if you were zoomed in really close and the linear approximation hugged the curve well, and then you added on top of that t sub 3, t sub 5, t sub 7, you wouldn't see much difference, right? They'd all hug the curve very well. But if you zoom, what happens is the higher the n, then the polynomial, the Taylor polynomial is going to hug the curve well for a larger range about the center point. That's the idea. Like, you can think about it like, no matter if with the linear approximation, once you get too far from the center point, it's like the air starts to fall off a cliff. It just balloons. Well, with every Taylor polynomial, that's the case. But the larger the n value, it's going to take, you're going to have to go farther from the center point before it starts to fall off a cliff. Okay, one use of the type of calculations done in these last two examples occurs in calculators and computers. For instance, when you press the sign or e to the x key on your calculator, or when a computer programmer uses a subroutine for a trigonometric or exponential or Bessel function, in many machines a polynomial approximation is calculated. The polynomial is often a Taylor polynomial that has been modified so that the error is spread more evenly throughout an interval. So yeah, what they're saying here is that if you take out your calculator and you just do sine of 70 degrees, that's it. You know, I'm not a programmer, but I think the idea is it will go ahead and it will use the actual definition of trig functions to give you a value. So it will, you know, we talk about this in the trigonometry playlist, but it will, you know, we'll probably use the unit circle, and it would, like, so at 70 degrees, it would dial in the angle numerically, and then it would, the coordinates of the point on the unit circle represent sine and cosine, so it would, like, numerically find those coordinates and give you a value, right? But let's say it was part of, like, a bigger operation, like a series of steps and just a lot of different functions going on in some calculation. Maybe there was a trig function inside of an integral, I don't know. Then instead of going through the entire definition of the trig function process, it might use a Taylor polynomial to the accuracy that's sufficient, because that's a lot quicker and easier. That's the way you can think about it. So yeah, I mean, the Taylor polynomials are used for so many more applications than you would initially think.